Okay, in this video we're going to have a look at how we can control the reaction that's part of the Haber process in order to make more ammonia. Okay, there's going to be quite a lot of science in this, so please watch the other videos to get the background, and then you might want to watch this video a couple of times just to really make sure that you've got it. Okay, so the first thing is, here's our equation, and you can see here that we've got the nitrogen and the hydrogen, and it's reacting to form ammonia, and this reaction is reversible. Remember, that means it goes in the forward and backward directions. The facts we need to know is, going in the forward direction, this reaction is exothermic. Remember, that means it releases heat energy, and therefore it's going to cause the surroundings to become hotter. And going in the opposite direction then must be endothermic, and that means it's going to take in heat energy, and therefore the surroundings are going to become cooler. So first observation, we need to understand the direction of exothermic and endothermic. Second thing to look at is, on this side we've got 1 mole of nitrogen and 3 moles of hydrogen, so there's 4 moles in total here. And on this side we've only got 2 moles of ammonia. Okay, so in terms of pressure in these conditions at the moment, remember, pressure, the higher the number of moles, the greater the pressure. Here we are going to have high pressure, and this side the pressure will be lower. Okay, and we're going to need that in a moment to understand these conditions. So the first condition I'm going to change is going to be temperature. And if I'm going to make a change on this reaction, let's just put this back underneath our work, then we need to remember Le Chatelier's principle, which says for reaction equilibrium, it will go against any change that we impose on it. Okay, teenager's law, do the opposite what we ask it to do. So if we're trying to decrease the temperature, this reaction says, according to Le Chatelier, it is going to increase the temperature. Okay, how is it going to increase the temperature? Well, let's go back to our reaction. If it moves in the forward direction towards the right, then the reaction gets hotter. So that's what it's going to do. So here I'm going to write down that the equilibrium will move to the right, because that is the exothermic side, and that's the reason. I'm going to put the reason here now, because it's exothermic in that direction. What will happen if it does that? This means the reaction is going this way, flying through here. Therefore we are going to get more, we're going to get an increase in the amount of ammonia. We're going to get more ammonia produced, which is good. That's what we want. Okay, so that's a good thing. So temperature, this reaction would favor a lower temperature to get more ammonia for the reasons we've just explained. Let's look at pressure, see if we can squeeze this in. Pressure, we're going to try and increase the pressure. Le Chatelier's principle says it's going to do the opposite, so it will try and lower the pressure. If it lowers the pressure, go back up to here, the side with the lowest pressure is the right hand side, so the equilibrium is going to move to the right to try and lower the pressure. So equilibrium will move to the right. Why is it going to move to the right? Because this side has fewer moles on it. Why is it doing that? Because there are fewer moles, and that means, because it's moving to the right, to this side where 2 moles are, we're going to get more ammonia. So we will get an increase in the ammonia, which again, that's what we want. So the condition of pressure, higher pressure means more ammonia, good. Lower temperature means more ammonia, good. So we are in a situation here where we can change these two conditions and we can get more ammonia. This can then be used to produce food, as we said earlier in an earlier video, and that's what we want to happen. But there's a problem. There is a problem, okay? Because if we lower the temperature, so the first problem is this reaction wants us to lower the temperature. If we lower the temperature, the reaction slows down. And if the reaction goes slower, we will get less ammonia. Not good. We don't want that to be the case. If we increase the pressure, there's a problem. These are all gases. These gases are being pumped around this system under high pressure, then what's going to happen? Pipes are going to start to burst because we're pumping the gas through at high pressure. So there's a cost issue here. Okay, there's a cost issue because those pipes that we want to push the gas through would have to be thickened to strengthen them, and that costs money. So the industry isn't really going to want to do that. So you're having a conversation with your boss, you're saying, do you know what, I remember some chemistry here, and I know that this reaction, we want to lower the temperature, we want to increase the pressure. And your boss is saying to you, no, you can't do that, because if we lower the temperature, it goes too slow, and if we increase the pressure, it's going to cost us money because pipes will be bursting all over the site. Two people, different points of views. What do you do? How do you resolve this? Well, what you do is you come up with what we call a compromise. Okay, you come up with two different views, you come up with a compromise of those views. And what you do is you use a temperature that is low, but not too low. We don't want the reaction to go too slow. And we use a pressure that is high, but not so high that it starts to cost us significant amounts of money. And here are the two conditions that we have. So we start with a temperature of 450 degrees as a compromise. So that is low, but not too low, so the reaction doesn't slow too much. We have a pressure that is 200 atmospheres. That means it's 200 times greater than the atmosphere that we're sat in at the moment, which is a high pressure, but not so high that we're going to have huge costs linked to the strengthening of the pipes. Then you're going to pull your ace out of your sleeve, because what we can then do to this is we can add an ion catalyst. And if we add a catalyst, remember catalysts cause reactions to speed up. They do that by lowering their activation energy. So we can cause the equilibrium to be set up faster, which is going to be a benefit to us. And the way they do this, I'm going to show you a little picture here to show you this is called the reaction chamber. And into the reaction chamber, you would pump in your nitrogen and your hydrogen, come in, and sat on these beds, these shells sticking out, you would have your ion catalyst. And what would happen is your nitrogen and hydrogen come in and they move. Notice how they have to move. They have to move all the way along here, passing over the ion, because that helps it to react. And you have to move all the way along this one and all the way along this one until they come out. And because they're getting lots of contact time with the catalyst, the ion, they will convert into nitrogen, hydrogen, will convert into ammonia, and we will start to get ammonia produced here. And that's good because these conditions are a compromise. The catalyst means that it become more effective at those conditions. So the catalyst is the third factor that we change in order to make this reaction work. Okay, you need to know the conditions. You need to know why we have these conditions. Why do we have to get that compromise, that balance to this reaction?